Hello, everyone. So in this lecture, I'm going to try to go over some of the main ideas or concept that will be covered in the first exam. So one of the exercises in exam one will be about the CPU scheduling that we've covered so far. So this is a practice exercise that I need you um, to try to practice before the exam. So for instance, I'm going to give you such a workload where we have here 5 different processes along with their arrival times and CPU times. And then I'll ask you to calculate the average waiting time and turnaround time using different CPU scheduling algorithms. So for example, the first one, which is first in, first out, or first come, first serve. So basically the main idea is processes get scheduled based on their arrival time. So if you want to draw a Gantt chart, so at time 0, we have to be careful and look at the arrival time always, right? So at time 0, I have P1, and first in, first out is non-preemptive. So once a process starts executing, then we do not have the ability, no other process has the ability to interrupt it. So at time 0, process P1 starts executing, and it needs 5 units. So from 0 to 5, P1 executes. The next one is P2. So P2 starts, so P2 arrived at time 1, right? So this is where P2 is, and then at time 3, at time 3, we got P3. And then at time 4, we have P4, and at time 5, we have P5. So by the time P1 is done executing, all of the other processes have already arrived to the ready queue. So now we can schedule them in the order that they arrived in. So right after P1, we got P2. So it needs to execute for 4 units. So from 5 to 9, this is P2. And then after that, we got P3. It needs to run for 2 units. So from 9 to 11. And then after that, we have P4, right? And it needs 3 units, 14. And lastly, we got P5. It has to run for 2 units, and that's 16. Okay, so this is the Gantt chart. And then we have to start by calculating the waiting time. So the waiting time individually for P1, it arrived at 0 and it started running at 0. So it waited for 0. P2 arrived at 1 and started executing at 5. So 5 minus 1. Okay. P3 started executing at 9 minus the arrival, which is 3. And then P4 started executing at 11 minus the arrival, which is 4, right? And then lastly, P5 started executing at 14 minus the arrival time, which is 5. So once you have the individual waiting times, you can calculate their average. That will be the average waiting time. And so for the turnaround time, it is equal. So turnaround time, it's equal to the waiting time plus burst time. So for instance, P1's waiting time is 0. So the turnaround time for P1, so P1's let's say this is turnaround times. So P1's turnaround time will be 0 plus the burst time, which is 5, right? So for P2, it will be the waiting time here of 4 plus the burst time of 4, that's 8, and so on. So once you calculate the individual turnaround times, then you average them, and that will give you the average turnaround time. So that's for FIFO. Okay, so the next scheduling algorithm is the shortest job first. And again, this is a non-preemptive algorithm. So again, I'm sorry. Let me erase this. So we start at time 0, right? And at time 0, so shortest job first is about picking the shortest next burst time, right? However, you need to pay attention again to the arrival time. Do not go straight to compare the CPU time, because, for instance, if I go directly to compare their CPU times, then I can see that P3 and P5 have the shortest burst times. However, these two processes have not even arrived yet to the queue. So P3 arrives at time 3 and P5 arrives at time 5. Okay, so do not make this mistake. Always check the arrival first. At time 0, the only available process in the ready queue is P1. So P1 starts executing from 0 to 5. Okay, so in the meantime, again, at time 1, I have P2. At time 3, I have P3. At time 4, I have P4. And then at time 5, I have P5. So by the time P1 is done executing, all of the other processes are already in the queue. So P1 is gone. Now I need to compare the burst time for the currently existing processes in the ready queue. So I can see that P3 and P5 have exactly the same burst time or CPU time. And in that scenario, I will use first in, first out to break the tie. So then P3 goes first. So it executes for 2 units. So from 5 to 7, so P3 is gone. And then P5 is next. So 9. And then lastly, I have P4 is the next shortest. This is P4. And then lastly, I have P2. Okay, so again, to calculate the waiting time, you have to check when did the process start running and when did it arrive, or in total, how long a process waited in the ready queue, right? So with non-preemptive algorithms like first in, first out, and shortest job first, it's very easy to get the waiting times. Simply when did it run minus when did it arrive. Why? Because with non-preemptive algorithms, we do not interrupt a currently running process. So once the process starts running, it will not go back to wait in the ready queue again, okay? So once it starts running, it will continue until it exits. So calculating the waiting time is fairly simple for non-preemptive algorithms, okay? So that's FIFO, and that's shortest job first. So let me clear this, and now let's do shortest remaining time. So shortest remaining time now is a preemptive algorithm, okay? Meaning we do have the ability to interrupt a currently running process. And so at time 0 again, right, I have P1. And then at time 1, I have P2. Okay, this is 2. At time 3, I have P3. At time 4, P4 arrives. And then at time 5, P5 arrives, right? So at time 0, the only existing process in the ready queue is P1. So P1 starts executing. okay? This is P1, okay? Now at time 1, P2 arrives. So this is a preemptive algorithm. So the scheduler has to stop and compare their remaining times. So at time 1, the remaining time for P1 now is 4. Let's compare it to the new arriving process, which is P2. It's also 4. And when you have a tie, you always favor the currently running process. So keep P1 running to save the context switching time, since both of them have exactly the same CPU time. So instead of context switching and adding that overhead of context switching, we're just going to continue running the current process who possesses access to the CPU. So P1 continues executing, and then at time 2, now the remaining time is 3. Sorry, let me click on this one and then go back. Okay, so now the remaining time is 3, and no arriving process at time 2. So let's continue to 3. At time 3, the remaining time is 2, and P3's remaining time is 2 again. So it's the same. We're just going to continue executing P1. And then at time 4, now the remaining time is 1. And P4's remaining time is 3. So the shortest is P1. Okay. And then at time 5, P1 is already done executing. Okay, that's 0. So now I have all of my processes already in the ready queue. So now which one has the shortest remaining time? So obviously P3 and P4. Again, to break the tie, I'm going to use FIFO. So P3 goes next at time 5. Right, this is P3. So it will execute from 5 to 7, right? And then 6, right? The next one is P5, okay, from 7 to 9, okay? So P2, P1 and P3 and P4 are gone. The next shortest is P4, right? P4 from 9 to 12, right? 12. And then lastly, we have the process P2, which will run from 12 to 16. Okay, so now to calculate their waiting time, you again ask yourself how long each process stayed. So this is P3, right? How long each process stayed in the ready queue. So you can see here that P1, as soon as it arrived at time 0, it started executing and it didn't got interrupted. So the waiting time here is 0. P3 had to wait for 5 units or 5 milliseconds, and then P5 started at 7. So it had to wait for this entire time since it arrived. So it arrived at time 3. So it waited from here to here, right? So you always have to do 5 minus when did it arrive, which is 3. Same thing for P5. It started at 7 and it arrived at 5. So it waited for this duration, which is 7 minus 5, right? P4 again started executing at 9, but it arrived at 4. P2 started executing at 12. It arrived at 1. Okay, so this is the individual waiting times, and then to get the turnaround time, always you add wait time plus burst time or CPU time. Okay, So let me erase this and get to the last scheduling algorithm, which is now round robin with a time quantum of 4. Again, this is a preemptive algorithm. Okay. Okay, so again, we're gonna try to keep track of when every process arrived. So at time 0, we got P1. At time 1, we have P2. And then at time 3, we have P3. At time 4, we have P4. And then at time 5, we have P5. Okay, so the only existing process in the ready queue at time 0 is P1. So P1 starts running at time 0. Okay, so remember our time quantum is 4. So every process will get to run for 4 milliseconds and it stops executing. Okay, so then from 0 to 4, this is 4 units, that's P1. And if this is our ready queue, so initially there was just P1, okay? And then by the time P1 is done, which is at time 4, we already have P2 in the tail of the queue, we have P3, and we have P4, okay? So P1 has run initially, now P1 is done, so it goes to the back of the queue. And then the next one to run is the process in the head of the queue, which is P2. So P2 starts executing from 4, right? This is 2. Do not forget to keep track of the burst times. So far P1 has run for 4 and it only has 1 unit remaining. So P2 now it will run from 4, 5. At time 5, we have P5 arrived. So we have to add P5 to the tail of the queue. Okay. So P2 will run from 4 to 8, right? And then the burst time is already now 0. P4 has already completed its total CPU time. P2 has already completed its total CPU time, so it does not go back to the tail of the queue. That's it. P2 is terminated. So the next in the head of the queue is P3. P3 will start executing. P3 needs a total CPU time of 2. So even though the time quantum is 4, P3 only needs 2 units. So it will exit at time 10. We will not put it again in the tail of the queue because P3 has already finished executing. The next to go is P4, right? And P4 only needs 3 units. So from time 10 to 13, that's P4, and it doesn't go back. And the next one in the queue is P1 at time 13. This is P1. P1 only needs 1 more unit, so from 13 to 14. And lastly, P5. Sorry, I only have a small space here. So this is P5. P5 has to only run for 2 units, so from 14 to, okay. So now again, you need to calculate the total waiting time for each one of these processes, right? So P1 initially did not wait at this point, but it waited here. So from 13 all the way to 4, right? So this is the waiting time for P1. So 13 minus 4. For P2, it was not interrupted, right? So it only waited for this period, 4 minus 0. This is the waiting time for P2. Same thing for P3, was not interrupted. It only waited from 8 to, so P2 arrived at time 1. So waited between this period to this period. P3 arrived at time 3. So it waited from 3 to when it started to 8 and so on, okay? So always make sure that you count all the time that each process went back to the ready queue. Okay, so here the only process that went back to the ready queue was P1. That's why we have to make sure that we take into consideration that it has already run initially here for the first time quantum of 4 units, okay? And again, to get the turnaround time, just add waiting plus first. This will give you the individual turnaround times, and then you average them. So the next exercise in the exam will be a matching terms exercise, meaning I will provide you with a list of terms along with a list of definitions, and you will need to match every term to the corresponding definition. Therefore, I recommend you to go through my lectures and write a list of each one of the key terms that we've discussed, and along with the try to understand the corresponding definition. So what is a scheduler, for example? A scheduler is a module, a hardware component that handles scheduling scheduling the processes, meaning it applies a scheduling algorithm to pick the process to be executed next. And then the second term can be, for instance, the dispatcher. What's a dispatcher? Dispatcher is another hardware component that handles context switching between processes. So once the scheduler has chosen the process to run next, it's the dispatcher that handles assigning that process to the CPU, meaning handling context switching, saving the old state and loading the new state, and so on. So try to review the lectures and understand all the key terms that have been introduced so far in the class. And then the next exercise in the exam will be about the different process operations that we've discussed, mainly about process creation using the fork system call. So try to review what we've discussed so far, the idea that we have a parent process that has the ability to fork to create a child process, and then the fork system call will return 0 to the child process and the PID of the child to the parent process, right? So that's how the parent knows the PID of the child, that using the return value of the fork system call. And then if it's a negative value, then that's an error. Okay, so try to review that part. And so this exercise will be mainly in C. So I may provide you with a C program and ask you to answer some sort of a question related to the fork system call. Okay. So that mainly covers most